next chapter, we have already completed all the exercises in the first chapter on rings. So this next is chapter 13 on integral domains, and here this is the first exercise. We have to verify that the first 8 examples given in the text are as claimed, that is, whatever have been claimed in these examples, they are true. So let's see the solution. We are going to write the statements given in those examples. Example 1 says this: the ring of integers is an integral domain. To justify this, we recall the definition of an integral domain. An integral domain is a commutative ring with unity which has no zero divisors, and a zero divisor in a commutative ring A, say R is a commutative ring and A is a non-zero element in R. If we can find an element B in R which is also non-zero, such that AB is equal to 0, then we will say that A is a zero divisor of a zero divisor in R. This B may or may not be equal to A itself. Okay, here we are not restricting, we are not putting any restriction on B, that B has to be different from A or anything like that. B may or may not be equal to A. So that's an integral domain. Now the ring of integers is an integral domain. We know that the ring of integers Z is a commutative ring. This we already know, because the multiplication of integers is a commutative operation, and there is a unity also, which is the integer 1. Okay, now to claim that this is an integral domain, we have to show that there is no zero divisor. For any two non-zero integers A and B, their product is non-zero. This is a property of the integers, and that's why this can never happen in the ring of integers. You take the product of two non-zero integers, that will again be a non-zero integer. Hence, this has no zero divisor. And thus is an integral domain. So that is the justification for the statement in example 1. Excuse me. Next example 2. I need ink. We see these things, these properties of integers and real numbers, often we mention them and we say that we are supposed to know these things, we know these things, and we just in a hand-wavy manner that it follows from the basic properties of the number systems. But if you really want to see why these things are true, we in fact have gone through all this in Analysis 1 by Terence Tao. I have those videos in this channel. You can check those things out if you want. So there we have in fact axiomatically constructed all these number systems, natural numbers, integers, and from that rational numbers, real numbers. Complex numbers we are yet to develop, but it will also come. Example 2. There we have in fact proved everything that for example multiplication of integers is commutative. This fact has been proved. Example 2, the ring of Gaussian integers. Which is denoted like this, and it is the set of all complex numbers of the form a plus bi, where a and b are integers, and addition and multiplication are those in the field of complex numbers. This is an integral domain. We know that the ring is commutative because multiplication of complex numbers is a commutative operation with unity 1 plus I 0 or 0I, whatever you prefer to write. This ring has no zero divisor since the product of two non-zero complex numbers, so it's exactly like this ring of integers one, is non-zero. So no possibility of having a zero divisor. Hence, this is an integral domain. You should note one thing, that these classes of rings, integral domain, field, of course there is, I mean, so far we have, what I have seen, the definition of field is, it does not change. Integral domains, however, some authors like Gallian is requiring that the integral domain contain a unit element, unity. Herstein, on the other hand, does not require this. For him, an integral domain is a commutative ring with no zero divisor. Unity may or may not be there. So there are some such things whose meaning is not the same everywhere. So if you come across a term like this, you have to be sure what it means in the text or wherever it is appearing. Okay, for us here in Gallian, integral domains always have unity, a unit element 1, which acts as the multiplicative identity. So this is the second one. Then example 3. A ring Zx of polynomials with integer coefficients. Is an integral domain. We know that this ring, like the ones before it, is commutative. With the constant polynomial 1 as unity. Let f of x comma g of x be non-zero polynomials in this. Okay, then okay, instead of arguing in terms of coefficients of the leading terms, we can in fact talk about their degree non-zero polynomials. Okay, to make things more clear, we can in fact write the expressions for these polynomials. Let f of x be a naught plus a1x etc. plus a n x to the power n and g of x be bn x to the power n. And you can understand that this n and m are non-negative integers. At least one ai is non-zero and at least one bj is non-zero. In particular, we can, if we see, there is no point in writing those terms where the coefficients are actually equal to 0. So we can in fact assume an to be non-zero. You may think that okay, then what about these terms? You see, since one ai is non-zero, if you start by considering this thing and then you continue as long as you get non-zero terms, you will get one non-zero ai because fx is a non-zero polynomial. So you consider the non-zero ai that appears last, and that one is this one. So an can be chosen to be non-zero. In other words, the degree of this polynomial is n. Like that, the degree of g is m, and n and m are non-negative integers, where an is non-zero and bm is also non-zero. Then in the product, the product of course will have many terms. You have to multiply the terms out, then collect the similar ones, add their coefficients, all those things you have to do, but we don't really need to concentrate on the whole product. We will only concentrate on the product of these two. Then in fx gx we have the term an bn times x to the power n plus n. And note that this power of x, x to the power n plus n, is only this one. No other term will contribute to this power. Why? Because in the other terms, what will you have? You have some power of x, x to the power I, and you have another some power of x, x to the power j. So I plus j. And because we are talking about the other terms other than these two, so I is less than n and j is less than m. So I plus j will be strictly less than n plus m. So no matter what you get from the other terms by multiplying them, you will never get x to the power n plus m. This is the only term where you have x to the power n plus m. Okay, so that is why here the coefficient is just this one, which is non-zero because we are multiplying two non-zero integers. This where an bm is non-zero. So that just means what? That there is a non-zero term in the product of the polynomials, that is fx gx. So it's a non-zero polynomial. Do you see that this thing is a direct consequence of the fact that the ring of integers itself is an integral domain, so it does not have zero divisors. So non-zeroness of these two things implies non-zeroness of this a and bm. So that is why the ring of integer polynomials with integer coefficients is also an integral domain, where a and bm is non-zero. Thus fx gx is non-zero. This shows that this ring has no zero divisor. Hence, this is an integral domain. So we have justified the remarks of example 3. Then example 4. In this one, we have this ring whose elements look like this: a plus b times square root of 2, where a and b are integers. You can compare this with the Gaussian integers. The Gaussian integers are obtained by attaching the imaginary unit I to the ring of integers. This one is obtained by attaching the irrational number square root of 2 to the integers. And that is why the form of the elements is also like what you have there. In place of a plus bi, we have a plus b square root of 2. And this ring is an integral domain. We know this is commutative because the elements here are, after all, I mean whatever we have considered so far, minus the polynomial ring, all the elements have been ultimately complex numbers, and the addition and multiplication we are considering are those of complex numbers, and these operations are all commutative. So that is why this is commutative with unity unity 1 plus 0 times square root of 2. Here also there is no possibility of having any zero divisor, because after all these are complex numbers and in particular real numbers, since the elements in in this ring Z root 2 are real numbers and the product of two non-zero real numbers is non-zero this has no zero divisor. Is there a hyphen? I mean, do we have a hyphen here? I forgot. Zero. I think we have. So this is an integral domain. Then example 5. The ring ZP or ZP of integers modulo a prime P is an integral domain. We know that this ring is commutative. With unity 1. Okay. Now let A and B be two integers here such that AB is equal to 0. You should understand that this AB is not the ordinary product AB of the two integers A and B. This is the product where we have used multiplication modulo P. So this really means that P divides AB. P divides AB. Since P is a prime, we have this or this. That's the property of primes. If a prime divides a product of some integers, then it divides at least one of them. But that translates into A equal to 0 or B equal to 0. So if AB is 0, then either A is 0 or B is 0. The contrapositive of this statement is if both A and B are non-zero, then AB is also non-zero, which means that our ring does not have a zero divisor. Thus, this has no zero divisor, hence this is an integral domain. So that is the fifth one. Then 6. Unlike Herstein's topics in algebra, Gallian's text has manageable exercises, so it does not immediately jump into unattainable, exercises which are so difficult that the solutions are almost out of reach. So it gives us a nice practice. Some of the things like these things may seem a bit mundane, routine and boring, but we have to go through all these things, because then only we will get a grasp of these things, a much better grasp. So the next one is 6. The rings that N of integers modulo n, where n is some integer. To avoid unnecessary complexity, we can assume n to be a positive integer, modulo n. And in fact, I think in the definition of Zn, this modulus n is taken to be a positive integer. There is no point in considering negative integers, because they will give you the same thing. Is not an integral domain. When n is not prime, okay, so let us now justify this. This ring is commutative like the other ones, and it in fact has that unity. So in order to show that this is not an integral domain, we have to then show that there is no, there is a zero divisor, at least one zero divisor. So we just concentrate on that. Let n be not prime, or if you want to write positively, let n be a composite integer. Then there exist integers a and b such that both of them are different from 1 and n in this manner, and their product is equal to n. So that means a and b are proper factors of n, and that's why n is not prime. Okay. Now a and b belong to our ring Cn or Zn. We can see that n does not divide a, n does not divide b, but n divides AB. N does not divide A because A is strictly less than n and it is greater than 1 also. Just like that, n does not divide B, but n divides AB because n is equal to AB. That is, A is not equal to 0. I mean, modulo n, A is not equal to 0, B is not equal to 0, but AB is 0. So, A is a 0 divisor in Zn. And just like that, B in fact is also a 0 divisor by definition. Hence, this is not an integral domain. Then example 7, 2 more are there. The ring of 2 by 2 matrices over the integers is again not an integral domain. Now here, unlike in example 6, you don't even have to consider 0 divisors because our ring is not a commutative ring itself. Okay, so there itself things stop. The above ring is not an integral domain since it is not commutative. To show non-commutativity, you take 2 matrices with integer entries and show that they do not commute. Since commutativity is something quite special, so if you arbitrarily take 2 matrices with non-zero entries, then most likely you will get non-commuting pairs. To make 2 matrices commute is that is challenging. So I have just taken 2 matrices here. One of them is 1 minus 1 row wise, if I say 2 by 2 matrices, 1 minus 1 0 2, and the other one is 2 minus 1 1 2. So let me first calculate this product. 2 minus 1 1, minus 1 minus 2 minus 3, 0 plus 2 2, 0 plus 4 4, and if we change the order 2 minus 1 1 2 1 minus 1 1 minus 1 0 2, then 2 plus 0 2 minus 2 minus 2 minus 4 1 plus 0 1 minus 1 plus 4 3. I have them calculated here also, so let me just see. 1 minus 3 2 4, 2 minus 4 1 3. If you are wondering why I am being so slightly paranoid about these calculations, as you may have seen many times that I stress a lot about simple calculations, it's because I am very bad with numbers. I cannot calculate quickly with numbers. With symbols I am okay, abstract symbols, but numbers they make me stop. I don't know why. Anyway, so you can see that these two matrices are different, so they do not commute, and hence the ring is not commutative, so no question of being an integral domain. And the last one is example 8. This direct sum is not an integral domain. Unlike the matrix ring, this ring is commutative because the factors involved here, or rather I should say summands, because it's considered a sum. These summands individually, which are of course the same, the ring of integers, that is commutative, so this direct sum is also commutative. And in fact there is this unit element 1 1 unity, but there are zero divisors, and that is why this is not an integral domain. Note that one comma 0 and 0 comma 1, don't forget what this thing is. This is the, as a set, this is the set of all ordered pairs of integers, and as a ring, it's a ring in which addition and multiplication are done component wise. When we add, for example, these two pairs, we add the first coordinates and also we add the second coordinates, like that for multiplication also. So note that these things, these elements belong to this ring and they are non-zero. But if you take their product, then because multiplication is done component wise, so we multiply the first coordinates and we also multiply the second coordinates, and that gives us the zero element. Thus 1 comma 0, say, let us say that is a zero divisor. Hence this is not an integral domain. It shows that if you have integral domains, then their direct sum is not necessarily an integral domain. And in fact, if you think a little about this direct sum, it will never be an integral domain. That is because you can always find such things now, where you can make even if more rings are involved, what you can do, from the first ring you can take one non-zero element, make the other coordinates 0, that is you are taking zeros from all the other rings. The corresponding n tuple, or whatever tuple it turns out to be, that n is the number of rings involved in that direction, you have that as one non-zero element in the direction. Another element, in that other element you take the first coordinate to be 0 and make one of the other coordinates non-zero by taking a non-zero element from another ring. So these two are non-zero elements, but their product will be 0, just like this one. So in such a direction, zero divisors can always be found, so none of them will ever be an integral domain, in spite of the fact that all of them will be commutative, provided the rings you have taken are commutative and provided the rings all have unities in them, so that you can take them together and form the unity of this direction. Okay, so hence this is not an integral domain. So that is the thing, that is the first solution. Let's solve one or two more, because if I stop here itself, then what shall I write in the description? Here we have solved exercise 1 and that's just it. Which of examples 1 through 5 are fields? The first one was the ring of integers. A field, let us recall, is a commutative ring with unity in which every non-zero element has a multiplicative inverse. And of course, the unity is not equal to the zero element, which however is the case in this book. In Herstein's book, unity can be zero element, but here that is not the case. 1 is always different from 0 for us. The ring of integers is not a field since 2 is a non-zero element. This does not have a multiplicative inverse. Multiplicative inverse where? In the ring. In the system of real numbers, it has the multiplicative inverse 1 over 2. The next one was what? The ring of Gaussian integers. The ring is not a field since this element does not have a multiplicative inverse. For example, 1 plus 2i belonging to this in this. Why? Because you see that okay, this is after all a complex number and it's a non-zero complex number, so we know that in the field of complex numbers it has a multiplicative inverse, and that inverse is nothing but the reciprocal. If you try to express these complex numbers in the standard form as a real part, I mean one having a real part and imaginary part, then we can do that in the usual manner by multiplying and dividing by the complex conjugate 1 minus 2i. So this will be what? 1 square plus 2 square, because minus I square will be plus 1, which gives you 5 in the denominator. So that means the real part is 1 over 5 and the imaginary part is minus 2 over 5. And this of course does not belong to the ring of Gaussian integers, because the real and imaginary parts are not integers. They are in fact non-integral fractions, rational numbers. This does not belong to this, and that is why there is no inverse, so it's not a field. In number 3, the ring of integer polynomials is not a field because this integer, for example, or if you there is an easier option. You can just take x has no multiplicative inverse in this. I want you to figure out why on your own. So what this means is that you will never find another polynomial with integer coefficients, that is an element fx here, such that this product is equal to 1. Okay, that you will never find. You try to think of why you can never find this type of f. Okay, so this I am leaving to you. The full justification I am leaving to you. So this is the third one. In the fourth one, this ring is also not a field. Because 2 plus square root of 2 has no multiplicative inverse. And the reason is similar to this one. So what you do, just like this one, you just consider the reciprocal of this real number and then rationalize the denominator. Here you have made the denominator real. Here you make the denominator rational by multiplying and dividing by 2 minus root 2. I think it's called rational conjugate, or it is called something. Okay, so 1 over 2 plus root 2, you multiply and divide by 2 minus root 2. You will see that ultimately what you end up with, that is again a number of the form a plus b root 2, but where a and b, at least one of them will not be an integer like this one. So the inverse will not be in the ring. Has no multiplicative inverse in the ring. I want you to provide the justification like this. Here also you have to do some work. These parts I am not providing. The fifth one, however, is a field. The ring of integers modulo p, where p is a prime number, is a field. So this is the only field among these 5 examples, and this is in fact one of the results in the text. So no need for any justification, you can just refer to that result. I think it is a corollary to one of the lemmas or theorems, I can't remember exactly, but that's just it. So this is the only field. Exercise 3. Show that a commutative ring with the cancellation property cancellation property under multiplication. Has no zero divisors. Okay, so let R be a commutative ring with the cancellation property. we have to prove that R has no zero divisor. Suppose R has a zero divisor. A. That means A is a non-zero element. We are now going to write the meaning. Thus, A is non-zero and there exists an element B also non-zero such that their product is 0. That's what it means for A to be a zero divisor. But then AB is equal to 0, and this can be written also as A0 because in any ring A0 is equal to 0. Since A is not equal to 0, the cancellation property which we have assumed is there in R implies that we can cancel A from both sides of this equation, obtaining B equal to 0, and this is a direct contradiction. This is a contradiction. So our supposition is wrong. That is, R has no zero divisor. That's what we wanted to show. And finally, let's just do one more. List all zero divisors in this ring. In this ring, can you see a relationship between the zero divisors in this ring and the units in that same ring? So the elements in Z20 are just these integers. sorry, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 and 19. Now the zero divisors are those which are of course non-zero and for which we will find another element so that the product of these two will give us 0. In this case, because the operation is multiplication modulo 20, so we want a product that is divisible by 20. So you can see immediately that all the even integers are zero divisors. Why? Because 2 times 10 is 20. So modulo 20, 2 times 10 is equal to 0. So 2 is a zero divisor, 10 is also a zero divisor. And because you will get a 2 from a factor 2 from every even integer. So you can multiply, for example, 4 times 10 is 40, which is divisible by 20. So multiplication modulo 20 with respect to that operation, 4 times 10 is 0. Like that 6 times 10 is also 0. So these are all zero divisors. (14, 16, 18). But 4 times 5 is also 20. So 5 is also a zero divisor. And because of that, 4 times 15, which in fact is 60, 60 is divisible by 20. So this is also a zero divisor. Okay, so these are, I'm writing this, I'm showing this thing in a very brief manner. You have to write all the things properly. Zero divisors. Okay, and then the author asks us about the units in this ring, that is those elements which have multiplicative inverses. 1 of course itself is a unit because it's the unity and its multiplicative inverse is itself. Okay, 3 is a unit because 3 times 7 is equal to 1. Actually it is 21, but modulo 20 it is equal to 1. So these two are units. Like that, 9 is a unit and its inverse is itself. 11 is also a unit whose inverse is itself. 13 is a unit and in fact its inverse is 17 and the inverse of 17 is 13 because their product is divisible by it's not divisible by 20, but their product is congruent to 1 modulo 20. So modulo 20 their product is equal to 1, and 19 is a unit because it is again an inverse of itself. So you can see that in this ring all the non-zero elements are either zero divisors or units. That is the relationship, and in fact this relationship continues to be true in any set, and one can prove this, and this is the next exercise, which however we will see in the next Gallian upload on rings. So I am ending, let me just see what I have said here is really the thing. 9, 11, 13, 17, 19, yes. So that means the non-zero elements are either a zero divisor or a unit, and never both, of course. So that's just it. If you want to comment on all these things, you can write in the comment section below, and you can mail me. The link will be in the description. And tomorrow we have again real analysis, where we are properly going to start the theory of infinite series, where of course first of all we are going to start we are going through finite series. So we will develop a theory for that, and then we will jump into the theory of infinite series. So that's just it. So see you tomorrow with analysis. Until this, this is me, Lucifer, signing off from a mathematical room. Have a nice night.